Mr. and Mrs. Evans. It's an honor for me to be here today. Thank you, Steve, for this very nice introduction. I was very honored when I was asked to give this lecture. I know it has a very big reputation. And then I'm a bit awed because when I look at the past lecturers, they speak of a much wider aspect of science than what I will do today. Today is an adaptation, or a shorter version. The Rankine lecture lasts 80 minutes, so I had to cut down quite a bit. But I hope that it will give you some taste of what we can do with reliability analysis aspects in geotechnical engineering. I have 3 questions that I'm asking at the start of the lecture is, how can reliability and risk concepts help to ensure adequate safety while achieving cost-effective designs? And what are the advantages and challenges of using such method? And then we have also this other question, why aren't these reliability and risk concepts more used today? The mathematics of it have been around for many, many, many years. So I have a strategy for answering these questions, and it is that I will try to present some examples that are so simple and so convincing that it will make you want to use these methods, and show that probabilistic and deterministic analysis are, in many cases, necessary complements to each other. The contents of the lecture, there are just a few basic concepts, and then these real-life case studies to show you how reliability analysis helped us make cost-effective designs. And they're picked a bit, some from offshore, some from a very short example of slide in France, and then a dam facility, and then a few words about the New Orleans levees. Then a few thoughts short on the observational method and how this can be related to Bayesian updating, and then some summary and conclusions. In terms of basic concepts, I will have just a few, but so that we speak of the same things with the same words. Risk, I've decided to call it as a function of the hazard and consequences, whereas the hazard is a probability of an event occurring, and the consequence is a function of what can be at risk and the vulnerability of these elements at risk and their cost or utility. And in there, it could be also loss of life. And in the picture is an example of a failure that happened on Christmas Day in 2006, because one had forgotten that there was a thin layer of quick clay at that location. Now, risk management has been formalized. This is the picture of the ISO standard, 2009, describing the risk assessment, which is the area in orange, which is the identification, the analysis, and the evaluation of the risk. Evaluation means comparing it with acceptable standards, which we will discuss a bit later. But what is new and important in this standard is the communication and consultation here, and the monitoring and review, which is to be an integral part and done all the time during the evaluation of the risk. And then we have this expression, risk treatment, at the bottom. This is the new word for risk mitigation. So just that's the word used in the standard. Now, when we do standard type of analysis, deterministic analysis, we have different soil parameters, we have some loads, and we have the geometry of the problem. These are input into a model, and then you obtain a safety factor. Each of the parameters are put in with one singular value, a deterministic value, and the model, you assume that the equation is correct, and you obtain the safety factor. And then you compare it to what is the recommended safety factor in a standard or a code. When you do probabilistic analysis, you do the same thing. It's not more complex. You have to have maybe a little bit more input data, but you input again the soil parameters, the loads, the geometry, but you describe them as a distribution of values, as a minimum value, the maximum value, and its mean. And then these distributed values are input into a model, And there we have one additional parameter, which is a model uncertainty. It means by how much you can be uncertain of how good the model calculates or predicts your condition. And then you obtain a safety margin, not as a function as one number like a factor of safety, but a distribution with different values and a range for them. And these are often expressed in terms of probability of failure or reliability index, or both. And here too, we have acceptance criteria as you compare the probability of failure with the target probability of failure, which is usually a number per year. Now, a very important aspect with respect to factor of safety, it's by tradition or regulation, one uses today a factor of safety which is a constant value for all type of situation, whether you have a lot of uncertainty or very few uncertainties. And that's because that's the way the codes are made. But it's very important to be conscious that you can have a situation with a factor of safety of 1.8, as in this case, which has a high uncertainty, so it will have a distribution like this, because of the uncertainties are large. And whereas you can have a factor of safety 1.4 here in this case, but very little uncertainty, so the distribution is perhaps like this. And if you calculate the probability of failure, the annual probability of failure for the two cases, it is represented by the zone where the factor of safety is less than 1. And you can easily see that the probability of failure in this narrow distribution is much smaller with a factor of safety of 1.4 than in the case where there's a factor of safety of 1.9. In fact, the first time we presented this diagram in the early 70s, it was a real case. It was a platform built on piles, which had been hit by a ship, and we had to evaluate what was a safety factor. And the second case, the safety factor was much lower, but there had been so many more site investigation was done after the accident that we had much more information and therefore much less uncertainty. And we need to be aware that whatever one designs, the probability of failure is never zero. So the people who are against doing reliability analysis say, well, if you don't calculate the probability of failure, then it's zero. That is not true. The probability of failure is always there, whether you calculate it or not. And you need to do it because there are uncertainties in our calculation. And this is a picture of a very dramatic bridge, pillar on a bridge failure due to a landslide in Quick Clay in Norway this February. And so whether you account for the geotechnical uncertainty, in any case, there were some uncertainties here. They were not accounted for in the original design. So now they have to pay several $1 million because the whole section of that bridge has been blown up and it will have to be rebuilt. So now we'll go to my examples. And the first one is the design of paths for offshore installation. And in this case, it's a method to design the path. And this is applicable to both jackets and to the new type of foundations for offshore wind turbines. And the motivation for this work, these are real life case studies, it's calculation we had to do. The guidelines today require that they call it in the standard, same level of safety for the newer, which we think are more reliable, design methods which are based on the cone penetration test, a CPT, as for the older American Petroleum Institute method. And the designer is required to choose himself what is an appropriate safety factor to use with these CPT methods. So our client, there was Statoil in this case, they could either choose to apply a conservative safety factors deterministically, and they had decided they would use 1.5, or try to document the level of safety with the probability of failure. So I'm going to show you very briefly design that was done at 3 sites. They are the designs where I will show you hold, and the platforms are being built. One of them is being installed this summer. 100-meter water depth, pipe paths 2.5 meters in diameter, so they're big. And in these 3 cases, the loading and compression was governing, so we look only at that. And the 4 methods that were used was the Imperial College, ICP, the NGI method, the University of Western Australia method, and the Fugro method. As you see, there are many methods with the CPT method, with the CPT penetration test. For the deterministic analysis, as I mentioned, Statoil decided to use 1.5. But for the probabilistic analysis, the target annual probability of failure was set to 10 to the minus 4. That's annual, and that follows the NORSHOC, which is the Norwegian standard for design of offshore platforms. It's also in ISO. Now, I have one theoretical slide. It's just in the calculations we'll make when we look at probability of failure, or we will look at the different distribution of factor of safety. How you do the calculation, I've illustrated with this two-dimensional plot. You write a function, for example, resistance minus load here, and then you define a zone where it is safe, where resistance minus load is greater than 0, it's safe, and where resistance minus load is less than 0, it's unsafe. The unsafe is the failure domain in pink, the safe domain is in blue. Now this is shown in 2 dimensions. Now you realize when you have an analysis with several soil parameters, they each have their uncertainty, it becomes a volume in as many dimensions as you have on certain parameters. So that's the theory of it. In one of the case studies, I show you the data we had on drain shear strength as a function of depth. And the data points are shown in red. All of these in this slide are from laboratory tests. And then the deterministic design done by an engineer from NGI, he chose the black lines as what we call the characteristic strength. This is what we use for calculation, like following the rules from the standard. And then we also show the mean plus or minus 1 standard deviation. And this study also helped us realize that the way we choose characteristic strength is maybe not very good. Look, why does this curve do this? Now, this was done by an engineer of NGI, so I take responsibility for it. But when you do a statistical analysis, you find out that maybe the profile should have been different. Here's an example. This is at the second site, site B, of what the 4-cone penetration method was giving as pile resistance and what the API was giving. The API is the black curve, and the 4 colored curves are the 4 CPT methods. And if you look at the depth of 60 meters down below, we have a value of resistance on the pile between 100 and 175 meganewton. That's an enormous difference, and it means a lot of money when you're going to install those piles offshore. Now, I mentioned that we need to have a model uncertainty. How do we obtain the model uncertainty for pile design? Well, this I've illustrated just with one example. Here's what we do is we define a model uncertainty from the results of pile load tests. Now, here is one for the pile diameter 2 meters. I showed this one because it was close to 2.5 meter. We have databases with, it depends on the author, but you have, let's say, 50 pile load tests in sand and 50 pile load tests in clay, which we consider good quality. And then we compare the result of the pile load test described by this point with the result that you do with the calculation using the profile at the site and your best estimate the parameters. And with 50, 60 data points, then you can obtain a mean and a standard deviation for the model uncertainty. There are uncertainties there, but still you use engineering judgment to help you. I have an example of the annual probability of failure calculated as a function of the pile length in the site with the clay. The pile penetration depth was 75, 80, and 90 meters. The deterministic design with the factor safety 1.5 with the characteristic strength that I showed you first gave 107 meter pile. You cannot penetrate 107 meter piles when you have a very dense sand layer at a depth of 90 meters. Then it was with new site exploration, then we were able to reduce 90 meter, but there too, it's very, very hard to penetrate such long piles. Remember, they're 2.5 meter in diameter. But these probabilistic calculations, including all the uncertainty in the parameters and the model uncertainty, which we gave quite large, gave you a probability of failure of about 10 to the minus 5 per year. for a penetration depth of 75 meters. Now, I skipped many calculations, and we also calibrated what was the safety factor, which is, we're doing some work in trying to change the codes, but I'm skipping that. But here I want to show you the consequences for the company Statoil, that they decide to use a probabilistic method to design rather than the deterministic one. And for the site A on clay, the pile penetration depth could be reduced from 90 to 75 meters. For site B, for 51 to 27 meters. It was a very, very bizarre site. As you went deeper, you weren't not gaining any strength, any resistance, because there was some sand, clay, sand, clay. And then for the third site, the pile length of 45 was reduced 36 meters. And the reduction in the deterministic pile penetration depth was allowed because it was documented that the probability of failure was less than 10 to the minus 4 per year. Naturally, well, just to give you an idea of the numbers, the company Statoil paid NGI, it's in kroners, but I don't know what's the conversion, but they paid us about 1 million kroners to do the calculation for each site. At the first site, that's the only one where I got the amount, they saved 60 million kroners. And naturally, I asked to have a part of the savings, but they said no. But, but it just showed that and when we can document that it's less, the probability of failure is less than 10 to the minus 4 per year, the authorities accept the design. The added value of the reliability analysis, the annual probability of failure of 10 to the minus 4 gave significant savings compared to the deterministic design. We also felt that, or we know that we can design with a much more uniform margin of safety, and we also were able to calibrate the safety factors, and this is research going on. And we also could document that the new cone penetration methods had less uncertainty than the API methods, so that's something that will be used further by the codes. But also what we learned is that the most significant parameter in all the analysis was the uncertainty, the model uncertainty. In the calculation of pile capacity, the uncertainty is very large. So we have to do more work in this area, and there's also a research project too on that. I'm going to quickly go through the debris flow in Barcelonnette Basin in France. I think it's just a few slides, and then go to the dams facility. And this is in the area in Barcelonnette, the Faucon catchment. And you can't read the scale at the right, but I can have it here. It's a very steep area. It's 3,000 meter elevation at the top, where the slide started. The buildings are shown in yellow in the valley. In pink, there are the power lines and the roads. And the area that you see on the graph is about 2.5 square kilometers. The problem was, what is the thickness and the velocity of the debris if the landslide reaches the village? And fortunately, we had 2 measurement points in A and in B, but we had to make a type A prediction. And in this case, we use Monte Carlo simulation. Monte Carlo simulation is a very good method if you're trying to predict means and standard deviation, not to predict 10 to the minus 4 like we did for the piles before. So I show you 2 results. And the first one is the thickness of the debris in point B. Point B was the one furthest down. And doing 5,000 simulation with Monte Carlo, those are shown with the block diagrams. And then we fitted that with the gamma distribution in red. And the measurements are shown with the arrows in blue, black there, blue here. And as you see, the values that are measured are close to the mean, and certainly within 1 standard deviation. And with respect to the velocity of displacing the debris, here too, the prediction was very good with the Monte Carlo simulation. Now, if you had done only 100 Monte Carlo simulation, you would not be able to get such a good result. And naturally, if you do 5 million, you would get even better result. The added value of these analysis, it has become a very good tool if what you're looking at is the mean standard deviation. But if modeling the tails of a distribution over there, at least our experience, we have to do 5 million simulations, and that takes a bit of time. But what we're using Monte Carlo simulation quite a bit is to experiment and develop develop the modeling of a behavior, for example, of a strain softening material, and to find out by how much you should reduce the peak shear strength in stability analysis when you have such type of material. So for such type of analysis, Monte Carlo simulation is very good. We go to the third case study, which is the design of a tailings containment facility in Romania. It's called a TMF, and the name of the dam is Corner Dam. It's a company called Gabriel Resources, a mining company wanting to exploit gold in Romania. And it has designed a tailings dam as shown here. It has a starter dam, this part here, then 2 downstream raises, and then the final dam, which is a very, very high quality rock fill, which is a bit exceptional for this type of dam, but also it's considering that when you have the tailings of a gold mine, you have all kinds of nasty stuff, including arsenic, which you do not want it to escape. There is also a secondary dam to catch any flow that might come, and the tailings are to be stored here. The starter dam is 90 meter high, and the final dam will be 180 meter high. And there is a very special requirement that there will always be a freeboard of at least twice the PMP, which is the the highest precipitation. So it's something that happens 10 to the minus 4, 1 in 10,000 years, and then it's going to be twice that elevation, plus 1 meter. It's very strict, but in the next slide, I explain what is the concern. We are in Romania. And the Baia Mare tailings dam in 2000 in Romania failed and released cyanide in water, killing tons of fish and poisoning the drinking water for 2 million people, not in Romania, in Hungary. So it's Hungary who's very concerned with this new dam. The Aznalcóllar dam in Spain, it released also 68 million cubic meter of contaminated material in the environment. And just recently, in 2014, the Mount Poly failure was the largest environmental catastrophe in Canada, and selenium and arsenic and many other pollutants were released. And in fact, we did this design of the dam several years ago, but as soon as the Mount Poly failed, we had to document what was the difference between the dam in Romania and the dam in Canada to make sure that the same thing would not happen in Romania. And for this analysis, we use the event tree analysis, and I'm going to say very little about it, but just say that it's a graphical representation of many chains of event. It's a what-if analysis. And we look at all these events which might result in a failure, and we look at the probability of these events occurring. So in Rosia Montana, the most important part in these processes is to screen the different types of failure. So we had to answer the question, what would happen to the dam and the population downstream and maybe the environment if there's an earthquake, if there's very, very large rainfall, if a slide occurred on the hillside into the tailings ponds, if the crest of the dam slumped, or 2 or more, these things would happen at the same time. And we even look at the possibility of a plane crashing in the dam or a terrorist attack. Although this is in Transylvania, this is where there are lots of vampires, but I don't think there's too many terror actions in the area. We look at all the plausible ones, but you realize that to the terror part, we put a very low probability of occurring. The evaluation was done by assembling dam specialists, geotechnical engineers, and risk experts from different countries. And then we look at all these failure modes from the start of the construction during the entire lifetime of the facility, which the construction lasts about 12 years, and then the deposit, so the life was 25 years. Then after that, there was a covering and a renovation of the entire area. We looked at the consequences from no consequences to small release of tailing to catastrophic release and contamination downstream, including loss of life. Quickly, different types of scenarios. I'm not showing all of them. All together, it's an enormous report, and there were 56 event trees, and each of these event trees are 3 meters long in paper. And this is done by a computer, but still, you have to put numbers on these. So this is a starter dam. You could have a failure through a weak foundation layer. In fact, that's what happened at Mount Pauli. You could have toe unraveling, which is not unusual, for example, if you have piping. You could have the more classical potential sliding from the crest on towards the downstream side. And for the completed dam, the corner dam, examples are slumping at the dam crest, as I mentioned before, that the tailings would overtop. The rock fill could fail inside the tailings, and then there would be another form of overtopping. Or again, we had Professor Morgenstern from University of Alberta on the group of experts, and he was very concerned. The dam is built in a valley. He was very concerned that the sides of the valley, one of the sides would slide it and would push the fill and then create a failure. After those 56 event trees, we came that for the starter dam, remember there was a very, very large freeboard, twice the probable maximum precipitation in 10,000 years, plus 1 meter. So there was no significant release of tailings for the starter dam because of the large storage reserve. However, as for most dams, internal erosion was the most critical. But all of that was released was contained by the secondary dam. It could contain 250,000 cubic meters. The corner dam, the highest probability of non-performance were from earthquake shaking, and liquefaction of the tailings and valley slope instability were slightly less probable, but still quite close to the earthquake shaking. And the physical impact, if the dam breach would occur, the tailings would flow about 200 meters past the secondary dam, 250,000 cubic meters of tailings and 26,000 cubic meters of water would escape. And then the water would discharge in the river that's nearby, and it would have some cyanide levels in it. And in some cases, it would be higher than what was allowed. This is if a breach occurs, if it doesn't occur. But these cyanide levels will be above what was permitted only when there's low flows, in the winter months, when there's ice, so there's little water flowing. When there's a lot of water flowing, then the levels would be acceptable. But what was the probability of failure on an annual basis by adding all the potential failure modes, because you don't consider only one, you have to consider all of them, and the total probability of failure is the sum of them. The highest probability of a breach occurring was once in 1,000,000 years, or 10 to the minus 6. This is a very small number, but it's a good number to compare to what else is normal for dams. And here I have put the data for the US dams, the blue points. This has been published in the literature. And the annual probability of failure based on observations and different calculations is somewhere between 10 to the minus 4 and 10 to the minus 5 per year. The Roșia Montana in Bulgaria, in Romania, was at 10 to the minus 6, 1 in 1,000,000 years. And we don't have a number in the literature for tailings dam, but what we know is they fail much more often than normal dams. So they are probably in this area. So this dam is much safer, but again, it had the slopes was 1 in 3 on the rockfill side and 1 in 2 for the starter dam, and it had very high quality rockfill. But then you can ask me, but why did Mount Pauli fail? That was a tailings dam. How can that fail? Well, there was an expert group, and it finished, the failure happened in August 2014, and the panel was already finished, completed its report on January 2015. And the failure in the foundation of the embankment was due to a weak layer that was undetected. But in addition, the biggest mistake is the over-consolidated clay became normally consolidated under the loading or the building of the dam or the fill, and this was not considered. And that is a major geotechnical first-year mistake. But the slope downstream for the rock fill was 1.3 horizontal to 1 vertical. Montana was 3 horizontal to 1 vertical. But the calculation, the expert group said, had the slope been flattened to 2 horizontal to 1, as proposed in the original design, failure would have been avoided. There was no performance monitoring, although that had been recommended. Then why did the Alsnal-Collar Dam fail? And the picture for this one is maybe a bit more complex, but still there was a factor that was very, very important. And it's illustrated here. The design is the red curve, or the red slopes, and what was actual on this side is quite similar, but look at this, much, much steeper. Who allowed that? The as-built construction cross-section was different from the design cross-section. The design cross-section was 1.8 horizontal to 1 vertical. Again, that's a bit steep. Usually we like to have 2 in 1 at least, but 3 in 1 is even better. But the downstream slope was increased to 1.23 horizontal to 1 vertical in 1985. And that was not check, not control, not change. The added value of the inventory analysis, it looks at all potential failure modes in a systematic manner. It uses engineering judgment, and it's not a very mathematical. There are no big complex equation except when you do a finite element analysis of the displacement and the stability and all that. But it can be used to diagnose potential problems. And then it provides a good mean, or a documented mean, to compare with other facilities of the same type. So we say often that probabilistic risk analysis of a dam is a systematic application of engineering judgment. And before we go to the next example, this brought a paradox in my mind. I work in industry, not so much in academic, although NGI is like in between. So, but time and budget constraint and competition on price bring down the budget for site investigation, for design, to a minimum, even when there are important uncertainties. Every time I make an offer, I am pressed by the client to come the lowest possible. And after I've sent in the offer, can't you reduce? Do we need 5 CPTs? But when a major failure occurs, there seems to be unlimited budget for site investigation, lab and in situ analysis, finding experts all over the world. I have read the Mount Poly report, it's about this thick, and I have never seen in the space of 5 months so many lab tests, in situ tests and analysis, finite element, all colors and everything done. And the expert group, there were 3 and 3 of them are friends, they could order what they wanted. So how do we convince clients? I hope there's a few clients here. More site investigations and more time are needed in design. And the observational method is the best insurance. And reliability assessment will help you to provide more insight. Now, my last real-life example is New Orleans levees. And you know the story of New Orleans. I don't have to tell you as much as I told in London. But as you know, New Orleans has a history of flooding and overtopping ever since, I think it's 1927 was the first time or so, and then there was in 1965 and again in 2005. So the Flood Control Act of 65 decided to provide a protection system. Could the failure have been expected and better managed with the help of probabilistic analysis? And I'm going to show you how doing some very simple things, you knew that the failure was going to happen. The levees, well, there's a disagreement about this too, but the levees were designed with a return period of 100 years. Some people say it's 200 years, some people say it's 70 years. Some people say, oh, we never thought about that. Okay, let's use 100 years. The probability of failure when it's designed for 100 years is 1 in 100, so 0.01. So what's the probability of a 100-year hurricane and overtopping of the levees for a person living the levees for 50 years. Let's say the person lives 70 years, maybe not born there, moves there at age 15, and then he lives there about 50 years. There's something very simple. It doesn't look simple, but it's easy to apply. It's the Poisson distribution. And it's an ideal distribution to describe the possibility of an event to occur any time during a period of time like 50 years. So we won't dwell more into this, but if I apply this equation with a 100-year return period, I get that the probability of at least this 100-year storm occurring in 50 years is 40%. That is very high. We never design anything with a probability of failure of 40%. And if the return period, to keep quiet the people that argue that it was 200 years, then the probability of failure is 22%. That too is too high. We never design a slope with 22% probability of failure. So there was significant probability of overtopping in any 50-year period. In comparison, the dikes in the Netherlands, you know, the Netherlands are below sea level, so they have dikes to protect them. They are designed for heights, flood heights, occurring once in 2,000 to 10,000 year return period. So it's not the same around the whole of Netherlands. And then the levees protecting the Rhine are set to return period of 1,250 years. That's different from 100 years. Now, the calculation I did for you, that was for one dike. There are 350 miles of dike in New Orleans. And if we assume that each dike is built 1 kilometer length at a time, what is the annual probability of each reach failing? And what is the probability of the entire system failing? Now, we're going to skip this calculation, but again, this is a very simple algebra where you find that the reliability of one dike and then several dikes in connection in the system is the product of the different reliabilities. So the probability of failure is 1 minus the reliability. So if you believe me, then you can calculate quite easily the probability of failure of several dikes together. So now I made this little table, the probability of at least one failure if the levee system, if we consider that they're 1 kilometer long, so they're 560 reaches, 560 kilometers, the probability using the equation which is correct, it's 0.99. So it was sure it was going to fail at some point. Then you can make other calculations with other different lengths of reaches, but it's still very close to 1. And then you can always use 1 in 1,000 years, and again we have a probability of failure of 0.43. But this is to illustrate that it was bound to happen. Now, when we do such analysis, we use often this plot, which is called an FN plot, which the annual probability of failure, the F and N the number of fatalities, but it could be also millions of dollars, or it could be radiation from a pollutant and everything. It's a consequence. But here we put number of fatalities. And it's a very good way of communicating and comparing different probabilities of the same facilities. And then we usually divide an area which is tolerable or acceptable and an area which is non-acceptable. We'll see a bit more of that later. And then what you want to do if you're too high in non-acceptable, you want to either reduce the consequence, less fatalities, or you can reduce the annual probability of failure or reduce the hazard, the probability of levee being overrun. Now here is how these curves, these FN curves, plot for the New Orleans levees. Now in blue first is the risk that is unacceptable above the blue line for major dams. And that is in many, many different countries, so it's not, but it's also in the US. The New Orleans levees in 2005 had the upper curve shown here, which is very high compared to this for them. And then with all the modification, improvement that was done, this calculation was not done by me, but by Bob Gilbert, who spends his sabbatical at NGI, and he graciously gave me this data. It was moved to the left correctly, reducing the number of casualties, but not really reducing the probability of this happening again. And the problem with New Orleans, it was evacuated. And there were and there are fewer people living here, but it's slowly being populated again. People are returning. One comment is in 2005, this was called the Hurricane Protection System. And in 2011, the authorities realized that they were not too realistic how this was named. So now it's called the Hurricane Storm Damage Risk Reduction System, which is a much better representation of what it is. So why is the risk higher for the New Orleans levees? What is considered as tolerable is not an absolute, but relative to the context of the cost and the feasibility of reducing the risk. And I was not in that study, so I can just report what Bob Gilbert told me. It was not considered feasible to achieve lower risk for a long levee system in an urban area. But there is an emerging question for me as an outsider, is should one have used part of the $18 billion that were used on measures to evacuate the people in advance of a storm to avoid fatalities or even with overtopping? Because if you're not prepared for an evacuation, it's going to be a real mess. Everybody will take their car and drive at the same place, and then there will be an enormous blockage. We saw that in Houston right after Hurricane Christina. But I would think that maybe there should be some system that is established to evacuate the people, because you know, with this type of design and this type of return period, there will be another flooding episode within the next 50 years. Quantitative risk assessment should be also used for the selection of the most appropriate risk mitigation strategy. The added value of this analysis is simple reliability-based analysis. They did predict that the failure would occur. And the long levee should be designed for very long return periods if you don't want to have an overtopping event. And then I would suggest that one use reliability analysis also to select what is the optimum mitigation measure. Just a few points about the observational method. In the example you've seen, several of them show that the failures occur due to a combination of factors, but one of those recurring factors is that construction was not followed as it was originally thought, and the changes in design underway were not documented or included in the original design. And this reinforces the importance of and the need of the observational method, which was in fact recommended by Terzaghi and Peck, and later by Peck in his Rankine lecture. And the abridged version of observational method is those steps, is exploration, site exploration, find the most probable conditions and the most unfavorable conditions. You design based on the working hypothesis, anticipate for the most probable condition, correct, like a mean value. You select the quantities that you observe. You calculate the values for the most unfavorable condition, and then you will observe those. Then you select in advance the course of action for every foreseeable deviation from the mean behavior. And then you measure, and then you modify the design as you go. Well, Bayesian updating is a tool for us geotechnicians. Bayesian updating the theorem, it provides you a framework to allow updating your original estimates with new information. So it's one way of changing your opinion in light of new information. Bayesian thinking was, for example, used by Alan Turing in solving the German enigma during World War II, for those of you who have seen the movie The Imitation Game. And a very small example, very quick. Even when you don't have any information that is useful, forget the equations, but you can calculate the probability of failure after n years of observation with no sliding. This is for an underwater slope we did in the Gulf of Mexico, but the equation is as simple as this one. The probability of failure is 1 over the number of years with observation with no failure plus 2. And for example, if you haven't seen no slides during 1,000 years, then the probability of failure is about 10 to the minus 3. haven't seen in 18,000 years, it's 10 to the minus 4 or so. And I'm just going to illustrate to you what does the Bayesian tell you. If you don't know anything about the slope, you don't know whether there's been a failure last year or 10,000 years ago, you know nothing, then you have what is called a diffuse distribution. There's as much probability that a failure will occur, a failure will not occur. So it's a probability of 0 and 1 is the same. But if you just know, you know that there's no failure that was observed the past year, then already you can change the probability of failure and you increase the probability with the lower probabilities of failure. And then if no failure has been observed during the past 3 years, then you will have distribution like this. And if it has no failure in the past 8 years, then it already becomes like this blue curve. And from this information, you can construct a distribution function of the probability of a failure occurring in one location where you have no or several observations of failure. And this one is the probability of slope failure if 2 slides were observed in the past 10 years at one location. And this was one of the banks in the Gulf of Mexico. And naturally, 2 failures in the past 10 years, it has a mean of 2. And then a standard deviation of 0.12, which is easily calculated with tables. Quickly, just I have 4 emerging topics of telling you where the new methods are going. One of the problems we have is how do we treat the very low probability, the black swans, the very low probability events with very high impact, like the Gulf, like the tsunami in the Sumatra Islands. And this is also mentioned in UN's IPCC extreme events report, so they mention us. And the emerging solution, there's a new method called stress testing. There's a lot of research being done on this in Europe, and that is the way we're going. The other issue is cascading hazard and risk. And before I tell you more about this, I want to show you what happened in the city of Bechuan after the Wenchuan earthquake in 2008. The magnitude of the earthquake was 7.9. It triggered 300,000 landslides, the earthquake, and 200 landslide dams were formed. It's a landslide that comes, it blocks some water, and then you have a dam. And they can overtop quite often. This city here was severely damaged. The decision was whether to evacuate or not. The decision was, after a study, was that to evacuate, and you will see now why this was correct. The earthquake occurred in 2008, May, and the landslide that followed. And then in June 2008, flooding. September 2008, debris flows due to the weather. And then in flooding again in 2013. So the decision to evacuate was correct. But how do we solve this problem? I showed you just one triggering event in my examples. So the emerging solution for this is we're using now Bayesian networks, which is a quantitative method, which is an advanced form of Bayesian updating, but using all the sources of possible triggers and combining sliding with flooding and such. And the probability and the risk are very different when you combine the sources. The third aspect is getting a value of acceptable risk. So I'm just showing here the comparison, the requirements in terms of FN curve, the same curve we've seen before, from different countries. And I don't know if you can read this, but we have Belgium is this funny one here. United Kingdom is the top one in blue, and European Community and Netherlands are the lowest one. Hong Kong and Australia have been doing a lot of work, and they have this red curve and the black curve. New South Wales is mainly for dams, Hong Kong is mainly for slopes. And you see there is some scatter, but still there's a value 10 to the minus 4, 10 fatalities might be something that people can agree on. But still, a lot of it is preliminary. And naturally, you have to note that when there's a large number of fatalities, this is unacceptable to most people, so then there's a detailed study done. And then the last emerging issue is communication. And being a good communicator today is one of the most empowering skills that we as engineers can have or can acquire, because we don't have that. It's something we have to learn. But I always say, if you can communicate something, you have to understand the subject, so we have to do the work beforehand. Probabilistic analysis is a tool to help you to learn how to communicate, because it has to go over the boundaries of just geotechnical or civil engineering. It also encourages foresight rather than hindsight. I'm coming to my conclusion now, and before I conclude on the probabilistic analysis, preparing for this, I prepared for a whole year, is from the standpoint of accountability. The geotechnical engineer finds himself in a particularly vulnerable spot. He or she works at the interface of natural condition and man-made structures. And often we have little hard information, and it's our judgment that is continually put to work. So we're called often, very often, this is my work, we have to identify and define situations that are potentially risky or hazardous, and to initiate a discussion on a decision on whether the hazards are acceptable or not. And it's often our responsibility, but we usually have very few tools to do it. So reliability approach do not remove the uncertainty, nor they reduce the need to use engineering judgment, but they provide a way to quantify the uncertainties and to handle them consistently. They also provide you a basis for comparing different alternatives. And what's very important, I had the graph in the original ranking lecture, but there was no time for that, but the site investigation, laboratory testing, limit equilibrium and deformation analysis, instrumentation, monitoring, and engineering judgment, they still have to be done. But they are part of us into being able to do some reliability analysis. So I feel that risk and probability tools have reached a degree of maturity and breadth that make them effective to use in practice. They provide more insight than deterministic analysis alone. They help reduce uncertainty and focus on safety and cost effectiveness. So integrating both deterministic and probabilistic analysis is probably the optimum, and it brings together the best of our profession, including the required engineering judgment from the geo practitioners and the judgment from the risk analysis proponents. So I still have a couple of slides. This is the picture of the same bridge that failed. I don't know if you can see it, but there's a pillar that failed, and this is the landslide that occurred. And it's just that there was a man, a farmer. He came with his bulldozer. He wanted to prepare to plant something, strawberries or something. And it was quickly, and nobody told him, and the whole thing went away, and he took the bridge. Deterministic analysis gave an impression of certainty. People, factor safety 1.5, oh, that's good. It's never going to fail. Probabilistic analysis complete the picture by making explicit the uncertainties and their effects. And for improved geotechnical practice, we need both. In closing, I have to quote Voltaire. My mother tongue is French. Doubt is an uncomfortable condition, but certainty is a ridiculous one. But then I wanted to also find a quotation for the British one. And so I found Rudyard Kipling, of all people, Nobel Prize winner in literature, very well-known novelist and poet and everything. And I don't know if you know that, but the ranking lecture, as mentioned by Steve, is very important in our profession. But I was the first woman in 55 years. And the whole week, there's a like celebration the whole week before and all that. The only thing he talked about is me being the first woman. Nobody mentioned that it was a great honor to give the ranking lecture. They just said the first woman, article newspaper, oh, the first woman. So I decided to revenge. Kipling said, a woman's guess is much more accurate than a man's certainty. Thank you very much.